Welcome. Here are some slides about simplicial complexes equipped with a function taking values in the complex plane, or more generally in a normed division algebra. So we have a set of sets, and we attach to every simplex a complex number or quaternion or octonion. This can be generalized much more. It can be a ring valued function. So we have somehow a ring space here. The complex numbers are the largest commutative normed division algebra, real, and the quaternions are the largest associated division algebra, and octonions finally are the last division algebra overall. So they are very natural objects. They are also very sweet. You can see that nature has built even sugar molecules around them, C6H12O6. The star and the core of a point can be thought of as stable and unstable manifolds with respect to the gradient flow given by the dimension functional. They are also very natural notions, so they are just defined in the simplicial complex. If you have all sets which are contained in a given set, so this is the core, and all the sets which contain a given set, this is the star. So it's a very natural thing, and then we can define matrices with them. So they kind of, if you think about them as stable and unstable manifolds, we can look at the intersections of stable manifolds, intersections of unstable manifolds, and this defines then the L matrix, which is the energy, the total energy of the intersection of the stable manifolds. And then we have also the G, which is essentially the energy of the intersection of the unstable manifolds. There's a conjugation with a omega, which is -1 to the dimension of x. So these are the two matrices, and here we see the matrices in the case when we have a complex valued field. So we took actually here circle valued h. So h takes values in the complex numbers with length 1. And so we have then the matrices, and in this case the conjugate of G is the inverse of L, so it's kind of green function situation. And these results were known kind of in special cases. I kind of generalized it now much more to division algebras. So first of all, we have the determinant is the product of the field values. So this is very general, doesn't even need to have a simplicial complex. It's true for any set of sets. And the energy theorem also is very general. We don't even need the full ring structure. We need only the monoid, additive monoid structure there. For the green star, we need that we have we take values in the units of the algebra. And this also generalizes to C star algebras when we have unitary operators. So we don't even need a division algebra there. And so this is justifying also why we can think about G as a green function, right, an inverse of a Laplacian. And so these are potential energies between two simplices. Now for the determinant, in the non-commutative case, one has to cannot take the Leibniz determinant because Cauchy-Binet doesn't work. So one has to generalize that, and Dieudonné has produced a beautiful determinant here, which is in the commutative case the same thing, but in the non-commutative case this uses the abelianization of the ring. So this is a non-commutative ring notion, but that holds here for the determinant. The study determinant is maybe more accessible because we just take the norm. We don't have to worry about abelianization. And in the non-commutative case, this is actually in the division algebra case, non-commutative case like H and O, this is what happens. Here we have the study determinant. So that's what I just said. So we have these 4 division algebras. There are 2 commutative ones and 2 non-commutative ones. In the commutative ones, we have the usual determinant. In the non-commutative one, we have the study determinant. Now, there's an interesting phenomenon happening in the complex plane. If you just move the energy value on a circle at one simplex. So I would have expected that the eigenvalues return to the original place, but actually this is not the case. There's a permutation happening, And so we have these different wheels. At every simplex we can turn this phase, and then we have we get permutation group, a finitely presented group, in general non-abelian group, which has a relation with a fundamental group of a Kähler manifold defined in this setup. It's very, very interesting and not studied. Here's just an animation which illustrates that. I show you just the imaginary part of the characteristic polynomial when I just turn the wheel, when I turn one wheel here. And so you see the eigenvalues which move around, of course, and then there's one eigenvalue which has actually kind of turned around 0. So all these eigenvalues are never 0 because the matrices are invertible. That's the magic of this whole setup. And just a few things. So this is very much in the flux, and I'm still working on this. Probably work for this quite a while more. There's something just discovered 1 or 2 weeks ago, which is a quadratic interaction formula, which is analog to the energy theorem, but it's a quadratic part. It's kind of an Ising Heisenberg type thing when you take simplices which intersect. So you can look at the energy values and multiply them. So this is kind of quadratic part, and there's a magic also going on here with the green function. There is still a formula which works, and so this is very exciting. I can prove that now, and this is relations with Wu characteristic in the case when h of x is omega x. So that's a very special case. But the Wu case is the analog of Euler characteristics. So the whole mathematics of Euler characteristics is huge. You know, there's a lot of theorems which deal with Euler characteristics, and they're all parallel with this Wu characteristic, quadratic. So there's a cohomology, there's everything, there's a calculus, everything kind of generalizes to this setup. And it's also kind of from a physical point of view, it's interesting, from statistical mechanics point of view. Especially then also if the h is just real valued, kind of a simple positive real valued, especially, and the eigenvalues are positive, and all the eigenvalues are positive. One can look at, for example, at the ground state. What is the smallest eigenvalue? So it's non-zero. And one can look at the relation between G and L and kind of make experiments. And so we have also density matrices if you divide out the trace, but divide by the trace, you get matrices with trace 1, which are called density matrices in physics. So it's interesting in many respects. And also from a statistical mechanics point of view or random matrix point of view, you can take all the field values and look at the probability measure on it, like a Haar measure in the case of unitary. And then look at what happens with the density of states, especially what happens with the density of states if you make barycentric refinements and we go to a barycentric limit. The limit exists. This density of states limits always exist by general principles. Here in a two-dimensional case, just a few barycentric refinement of a triangle. And we just look at the radial distribution of the density of states in a log scale. So this universality thing is very general, much easier than in a Van Hoff limit case when you have a lattice case, because what happens when you have in a barycentric refinement thing is that the boundaries have smaller dimensions, and these are the interfaces between different things, different patches which grow much faster than the interfaces, and so exponentially faster, and so one can prove relatively quickly that there is a universality here in very, very general frameworks. Now, also interesting is the isospectral story, a kind of what one can get isospectral cases by doing deformations. But here the deformations of the matrices, by Lux deformations of the matrices, is a very interesting story from a numerical point of view, because in general you converge to a diagonal matrix scattering situation. But it doesn't have to be a scattering situation. It can also be almost periodic, like in the Toda case, periodic Toda case. But it's a very interesting case. So here kind of just is a little animation which shows kind of what happens when we take H positive valued only, or H positive or negative valued, and we look actually what happens with these matrices when they this is unexplored, but it's an integrable systems. Eigenvalues are integrals of a motion. So we would also like, of course, to have more relations between the topology and this age-valued fields, probably after averaging, or understand the isospectral thing, so which age produces the same eigenvalues. And also interesting, of course, is this permutation story of the eigenvalues in the complex plane, which is this game. We don't know what these groups, what possible groups we can get there. So that's it. And so I have a project page, and this is a write-up about this determinant and division algebra story.